Okay, so we will begin by recalling what we have done yesterday. So what have we done yesterday? We discussed briefly the improper integrals of the second kind and the third kind. A combination of first and second kinds are improper integrals of the third kind. We discussed the Cauchy principle for that, we discussed the comparison test for that, and there were quite a few exercises for you to do. And the last one was the improper integral test. So if you have a monotone decreasing function which is non-negative, then integral 1 to infinity ft dt and sigma fn n from 1 to infinity behave alike, that is both converge or both diverge, right. And then we moved on to the discussion of the gamma function. So we briefly touched upon the historical aspects of the subject. And what is the definition of the gamma function? Integral 0 to infinity e to the power minus t to the power a minus 1 dt, correct. And this improper integral converges when a is positive. You can allow the a to be complex provided real part of a is positive, correct. So you get a function defined on the right half plane or the positive real line, depending on whether you want to stick to the real case or the complex case, correct. On the right half plane, this function is an analytic function, right. On the right half plane, the gamma function is an analytic function. A single integration by parts gives you gamma of a plus 1 equal to a gamma a. Putting a equal to 1, you directly calculate that gamma of 1 is 1. From these two, it follows that gamma of n factorial is what? N minus 1 factorial. So excuse me, gamma of n equals n minus 1 factorial. So gamma 2 is again 1, gamma 1 is again 1. Right? The gamma function takes the same values at 1 and 2. Right? Gamma n is n minus 1 factorial. What is gamma half? It is root pi, right. And so by the functional relation, gamma 3 by 2 is half gamma half. Likewise, you can calculate gamma 5 by 2, gamma 7 by 2, etc. So the values of the gamma function are known explicitly at the integers n and at integers plus half, 3 by 2, 5 by 2, etc. These are the only values for which the gamma values are known precisely, correct. Just like the sine function, you understand sine pi by 4, you understand sine pi by 3, you understand sine pi by 6, but you do not know what is sine 1, right. The rational multiples of pi are pretty much the only thing you can ever hope to understand, like pi by 5, you can sine of pi by 5, you can compute sine of 18 degrees, which is sine of pi by 10 you can calculate, etc. So there are the values of sine function are known only for special values of the angle, right. Sine 1, you have no clue as to what it is, you know it is transcendental, that is all, otherwise you do not know much. Similarly, gamma function is not known at anything else other than integers and integers plus half, correct. The next thing that we started discussing was the characterization of the gamma function in terms of the functional equation. So we saw that f of x plus y equal to f of x into f of y is a functional equation. If f is continuous, then you can show that f of x is e to the power cx, and the moment I prescribe the value of f of 1, c is pretty much fixed. That is a normalizing condition. Prescribing the value of f of 1 is a normalizing condition, correct. Similarly, you can ask whether the functional equation f of x plus 1 equal to x f x together with the normalization f of 1 equal to 1 uniquely singles out the gamma function. Answer is no. Simple reason is that gamma x into cosine 2 pi x also satisfies the functional equation and also satisfies the normalization. So some additional condition needs to be put on the function f so that it singles out the gamma function. Is that correct? There are two such theorems available in the literature, one on the real domain and one on the complex domain. So, let us take the case of the real domain first. So, f from open interval 0 infinity to open interval 0 infinity is given function f of x plus 1 equal to x f x, f of 1 equal to 1. Then if f is assumed to be log convex, then f of x equal to gamma x. The additional condition that you need in the real domain is the log convexity of the function. What is log convexity? It simply means that log of f of x must be convex. So, f of x plus 1 equal to x f x, f of 1 equal to 1 and log f x must be convex. Since we are taking the logarithm, I am going to assume that the function is positive real value and the function is defined on the positive real axis. Right. So, the log convexity is the additional condition that is required to single out the gamma function. This is the Bohr-Mollerup theorem proved in 1922, correct. This is in the real domain. Now, let us come to the complex domain. So, now you have a analytic function defined on the right half plane, right, which satisfies the condition f of z plus 1 is z f z and the normalization f of 1 equal to 1, correct. The additional condition that is required of f so as to recover the gamma function is that mod f should be bounded in a vertical strip of width 1. So, this vertical strip we can take conveniently to be the strip 1 less than or equal to real part of z less than or equal to 2. Take a vertical strip of width 1, real part of z is between 1 and 2, both ends included, and you postulate that mod f z is bounded in this vertical strip, then f of z is gamma z. So, the additional condition that is required besides the functional equation and the normalizing condition is the boundedness of the function in the vertical strip of width 1, namely 1 less than or equal to real part of z less than or equal to 2. Is that clear? This is the theorem of Helmut-Wieland, the same group theorist Wieland. Wieland's discoveries in group theory and matrix analysis are far more deeper. They are very deep theorems in group theory he proved, and they are such deep theorems that this result in gamma function was completely forgotten. I mean, it is completely masked by his remarkable work in group theory until 1996, when Remmert brought into prominence and wrote a paper in the monthly in 1996. Okay. So, this is Wieland's theorem, and Wieland's theorem is not difficult to prove. The proof is available in Remmert's paper. It is also available in Remmert's book, which is cited in the monthly paper that I have given you. I sent everybody a PDF file of the paper. You can look at the list of references and you will find the references to Remmert, and the book of Remmert contains the proof of Wieland's theorem. It is very easy. You can actually teach it in a complex analysis course, and I often teach it here in the undergraduate complex analysis course. The proof of Wieland's theorem is done in detail. It is a nice application of Liouville's theorem. Okay. All right. Now, let us look at an application of Wieland's theorem. Our first application of Wieland's theorem is the duplication formula of Legendre. Right. You must have heard about the duplication formula and you may have seen it somewhere, though of course if I ask you what it is, you won't be able to remember it, and it's not fair to ask you to remember the duplication formula. I don't think if I were asked I could remember it. So, the duplication formula of Legendre. Legendre proved this in 1809. So, as an application of Wieland's theorem, let us prove the duplication formula. Root pi gamma 2a equal to 2 to the power 2a minus 1 gamma a plus half. This is a remarkable formula. I will tell you why it is remarkable later. First, let us get through with the proof. The formula can be rewritten as root pi gamma a equal to 2 to the power a minus 1 gamma a by 2 plus half. Please note, don't write all the details, just write the duplication formula. That is all that you really need for your exercises. The proof, you just listen, you try to take it in, and either by today or latest by tomorrow, I will upload it in your Moodle and you will have it. Okay? Because if you write, you can't listen and you cannot concentrate, and this is not easy to follow. The details of the argument are going to get more and more difficult, right? You are going to have copies of this, don't worry about it, in your Moodle. You can get PDF files. So let us define f of z to be 1 over root pi into 2 to the power z minus 1 gamma z by 2 plus half. So send the root pi to the right hand side and define whatever is the right hand side as your f of z. What are you supposed to show? You are supposed to show that f of z is gamma z, right? And the job will be done. How will you show that f of z is gamma z? First check that it satisfies the functional relationship. That is what you see on the last two lines. F of z plus 1 is 1 over root pi. The 2 to the power z minus 1 has become 2 to the power z, correct? And so you see that the last factor gamma z by 2 plus half has become gamma z by 2 plus 1 now. And now use a functional relationship and a z by 2 comes out, and you again see, lo and behold, you get z f z on the right hand side. So the function that we have defined satisfies the functional relationship. It is an exercise for you to check that f of 1 is 1. That is an exercise. Now what are we supposed to show? Third condition, mod fz is bounded in a vertical strip of width 1. Okay, let us turn to that now. Alright, mod fz is there on your screen. Mod fz is 1 over root pi mod of 2 to the power z mod of gamma z by 2 mod of gamma z by 2 plus half. 2 to the power z is what? E to the power z log 2. So what is mod of 2 to the power z? 2 to the power real part of z, which is x, correct? And then for the gamma parts, put the integral definition and take the modulus inside the integral. Mod of integral of f is less than or equal to integral of mod of f. And the moment you take the mod sign inside, you will again see a t to the power z type of business, and the mod of t to the power a will be t to the power real part of a, correct? So you get a less than or equal to sign, 1 over root pi 2 to the power x integral 0 to infinity e to the power minus t to the power x by 2 minus 1 into integral 0 to infinity e to the power minus t to the power x by 2 minus half. Now where is your x? What is that? That is nothing but gamma x by 2 and gamma x by 2 plus half, correct? Now where is x running from? 1 to 2. So x by 2 is running from where? Half to 1, closed interval half to 1, right? Gamma function is a continuous function on the open interval 0 to infinity, and so on every closed sub interval you have a continuous function which is going to be bounded. So by continuity, gamma x by 2 is going to be bounded when x runs from 1 to 2. Same is the case with gamma x by 2 plus half, and so that business is bounded. Finished, easy, pretty simple. And so by appealing to Villand's theorem, you get that f of z is gamma z and the duplication formula is completely established, correct? 2 to the power? There is a mistake, 2 to the power z minus 1, isn't it? Okay, the previous slide. Yeah, that is correct. It is 2 to the power z minus 1. Alright, 2 to the power x minus 1, x minus 1, x minus 1. This becomes a 2. Is that correct now? Okay, thank you. This is a 2 to the power z minus 1. I made a mistake. It's not, but it is still bounded, and that's all that we are bothered about. Okay, so the conclusion is that by Wheeland's theorem, f of z equal to gamma z, that is the gamma z is 1 over root pi 2 to the power z minus 1 gamma z by 2 gamma z by 2 plus half as asserted. Later on, we shall give another proof of the duplication formula that does not use Wheeland's theorem, independent of Wheeland's theorem. We shall give a second proof of the Wheeland's theorem. Clear? All right. Let us proceed further. The beta function. What is the beta function? I am sure some of you must be at least familiar with it. Beta of AB equal to integral 0 to 1 x to the power a minus 1 1 minus x to the power b minus 1 dx. That is the beta function. All right. So, this is the value of the beta function is the integral 0 to 1 t to the power a minus 1 1 minus t to the power b minus 1 dt, a positive b positive. Please quickly write down these 4 exercises. The beta function has certain obvious symmetry, beta of ab equal to beta of ba. That is pretty obvious. The second result is also easy, you simply integrate by parts. The third result, think about it, and once you get the third result, combining the 2 and 3 you get 4. 4 follows from 2 and 3. And the last one is beta half half, it is elementary. You can actually perform the integration, correct? These are the 4 basic beta function identities. The first one and the fourth one are the most important ones in this. The first one and the fourth one are the most important ones, correct? This is a beta function. So, what do you know about the beta function? Is it related to the gamma function? It is related to the gamma function. The beta gamma relation is very famous. It is almost like everybody knows, everybody here seems to know the beta gamma relationship. One wonders, why should you even worry about the beta function? After all, it can be reduced to the gamma function. It is a surprising thing. Both these functions have existed at for a long time, and although all using the beta gamma relationship, all identities becoming involving beta function after using the beta gamma relationship become trivial. Nevertheless, the beta function has had an independent existence for a long time, and that's the way it is. And here is the beta gamma relationship. Gamma A, gamma B equal to gamma A plus B into beta of A comma B. Yeah, you can see it here. Gamma A into gamma B equal to beta A comma B into gamma A plus B. We shall prove this later in the chapter on Laplace transforms. So, Laplace transforms will be a long chapter. We will probably do it for, definitely it will span at least 2 sessions, and we shall see applications to differential equations. And I am not going to take the viewpoint that Laplace transform is some tool for solving this differential equation and that differential equation. For me, it is a very interesting object in itself, and one of the and we shall see as an application of Laplace transform, the convolution theorem, we will recover the beta gamma relationship. So, Laplace transform is a well worth studying for its own sake, not just as a tool for solving some initial value problem for ODEs. Okay, so that is an important application, no doubt about it. Here is another exercise for you. beta a comma 1 minus a equal to integral 0 to infinity t to the power a minus 1 dt by 1 plus t. Beta of a comma 1 minus a equals integral 0 to infinity t raised to the power a minus 1 upon 1 plus t dt. A simple change of variables will give you this result, alright. Please do this exercise, we are going to use this exercise very frequently. Now let us give a second proof of the duplication formula of Legendre. Let us begin with beta AA. Once again, don't write, you will have it all, but just follow the main steps. Just try to remember the main steps. So what is beta of AA? It is t to the power a minus 1, 1 minus t to the power a minus 1. You will naturally put t equal to sine squared theta. And this becomes 2 times integral 0 to pi by 2, 2 sine theta cos theta raised to the power 2a minus 1. Correct? So now let us multiply the whole thing by 2 to the power 2a minus 1, and you understand why I am multiplying it, because I am going to use the identity 2 sine theta cos theta equal to sine 2 theta. So now I am having an integral from 0 to pi by 2 sine of 2 theta raised to the power 2a minus 1. The next obvious step is to put 2 theta equal to t, rescale the angle, and it will simply become an integral from 0 to pi sine to the power 2a minus 1 t dt. Now the sine function is an arch starting from the origin and finishing at the point 0 pi. This is a symmetrical arch about the line x equal to pi by 2, right. So the integral from 0 to pi will be the integral from 0 to pi by 2 plus the integral from pi by 2 to pi, and the integral from pi by 2 to pi will be the same as the integral from 0 to pi by 2. Geometrically you can see that, or analytically also you can prove it. And so what do you get? You recover the 2 ultimately, and the integral goes from 0 to pi by 2 sine to the power 2a minus 1 theta d theta. But the right hand side is again beta of a comma half. So now you see that 2 to the power 2a minus 1 beta AA is the same as beta of a comma half. Now it is very clear what we are going to do now. We are going to apply the beta gamma relationship. Apply the beta gamma relationship and cancel off the gamma A, because left hand side you will get beta A is what? Gamma A into gamma A divided by gamma 2A. Right hand side is going to be gamma A into gamma half upon gamma A plus half. I am going to cancel off the gamma A. How do you know that gamma A is not 0? Gamma A is positive when A is a positive real number. What happens when A is a complex number in the right half plane? Then it is not so obvious, correct? Then it is not so obvious. That will not work. You cannot give an elementary argument from the integral that gamma A is not 0. It is true, but not so easy to prove. It is not so obvious. It requires work. Right? In fact, this point was raised. This point was raised by Stieltjes in a letter to Hermite in 1896. And Stieltjes did make an attempt to prove this directly, and the proof is quite non-trivial. It appears in one of the letters of Stieltjes to Hermite. It is referred to in my paper. You can look at it. So using the beta gamma relationship, you see this 2 to the power 2a minus 1 gamma a squared upon gamma 2a equal to gamma a gamma half upon gamma a plus half. Gamma half of course is root pi. gamma A cancels out. Let us assume that A is real and A positive, because you are cancelling it. And so you get the duplication formula for the real case. How do you get it for complex case? Now both sides are analytic functions and they agree on the real line, so they must agree everywhere. Correct. Both functions are analytic in the right half plane and they agree on the real positive real line, so they will agree on the half plane. So from the real case you can pass on to the complex case. Putting A equal to 1/4, we get a very interesting formula. Gamma 1/4 into gamma 3/4 is pi by sine pi by 4. This is a very remarkable formula, and this is actually a very special case of a very general formula, and now we are going to pass on to this generalization of this. Okay. And this generalization is called the Euler's reflection formula. Gamma A into gamma 1 minus A is pi by sine pi A, where 0 less than A less than 1. Several proofs are available for this Euler's reflection formula. Several proofs are available. Correct. And here I am going to tell you something. Just write the formula, please. Don't write all the comments. What is the left hand side? Beta A comma 1 minus A, correct? And we already done one problem on that, right? By change of variables, it is integral 0 to infinity. The left hand side is integral 0 to infinity t to the power a minus 1 dt upon 1 plus t, correct? Is that correct? Integral, please listen, integral 0 to infinity t to the power a minus 1 dt upon 1 plus t. Now suppose if a is a rational number, say p by q, then what does this read? This is t to the power p by q minus 1 upon 1 plus t. Suppose I put t to the power 1 by q equal to u. Let me just work it out separately on a rough sheet for you. So you have beta a comma 1 minus a equal to integral 0 to infinity t to the power a minus 1 t upon 1 plus t, correct? And I am assuming that a is rational, p by q, right? And you put, and so b of a 1 minus a equal to integral 0 to infinity t to the power p by q minus 1 dt upon 1 plus t. What happens when you put t to the power 1 by q equal to u? You will get t equal to u to the power q, and the numerator becomes u raised to the power p minus q, and dt will also be written in terms of an integer power of u, correct? So what happens totally? It is a integral from 0 to infinity of a power of t, integer power of t, divided by 1 plus integer power of t. In other words, the integrand is a rational function. When a is a rational number, we have just now seen that the integrand becomes a rational function after suitable substitution. Now you are integrating a rational function. This problem is completely elementary. You can actually carry out the calculation. Of course, This means you have to do partial fractions. This means that you have to factorize the denominator, correct? All this job is required. You need to factorize the denominator. The denominator is 1 plus u to the power q. So, you need to factorize 1 plus u to the power q, but that is easy because you know the roots of 1 plus u to the power q. The qth roots of minus 1, correct? And you can calculate the partial fractions, and they are all simple roots. So, the partial fractions decomposition is pretty easy, and you can actually carry out the calculation in detail. It is quite elementary. You have to do it systematically and carefully, otherwise you are going to get into a severe mess. But if you do it, you will get the answer, and you can actually prove the Euler's reflection formula for rational values of A. Now, both sides are continuous functions, and they will agree, you will end up proving that gamma A into gamma 1 minus A is pi by sine pi A for rational values of A. Both sides are continuous functions and they agree at rationals, so they must agree everywhere. This is one way of proving the reflection formula, the most elementary proof. This was done by Dirichlet. This was done by Dirichlet in his book on definite and indefinite integral in one and several variables. Other popular proofs involve contour integration, correct. So, in the letters exchanged between Stieltjes and Hermite, Hermite was trying to prove the non-vanishing of the gamma function directly from the integral relation, and he saying that it follows trivially from the Euler's relation, right. Gamma A into gamma 1 minus A is pi by sine pi A. From this it follows that gamma function cannot be 0. But arriving at the Euler's reflection formula is non-trivial. That is why Stieltjes was interested in this problem. And he mentions in his letter that this follows trivially from Euler's relation, but Euler's relation itself is not easy to prove. In response, Hermite sends a letter to Stieltjes where he gives an elegant demonstration of the Euler's reflection formula, for instance. So, that is another proof of Hermite. You can use a keyhole contour in complex analysis and prove the Euler's reflection formula. You can use the infinite product factorization for the sine function to prove the Euler's reflection formula. There are a variety of proofs available. Okay. A very remarkable proof was given by Dedekind in his thesis. I told you that Dedekind wrote his thesis under the supervision of Gauss. He was the last student of Gauss, 1854. That was 1854. I think Gauss died in 1855. We shall see Dedekind's proof in detail. But before that, let us look at, now that we have related the gamma function with the sine function, correct. So, what is the sine function? Sine function satisfies a very interesting identity. Sine 2x is 2 sin x cos x. Cos x can be written as sine of x plus pi by 2. So, instead of writing x, let us write pi x. So, we will write sine 2 pi x is 2 sin pi x sin pi into x plus half. So, sine function satisfies this very interesting duplication formula, and compare the duplication formula for the sine function with the duplication formula for the gamma function. You see a very close resemblance. The reason why there is such a thing is because the reflection formula tells you that the gamma function contains half the information that is contained in the sine function. The cosecant pi a, pi by sine pi a is gamma a into gamma 1 minus a. So, gamma a contains half of the information from sine function, gamma 1 minus a contains the other half. So, and it's multiplicative relationship. So, duplication formulas for sine, there is an analog of that for the gamma function, which is very interesting. Well, the sine function also satisfies this relationship, sine pi x, sine pi plus pi into x plus 1 over n, etc. Sine of pi into x plus n minus 1 by n equal to 2 to the power 1 minus n sine n pi x. Sine has this factorization also. What is the corresponding gamma analog if one exists? Lo and behold, an analog exists. It is remarkable, and it is a formula given by Gauss in 1812 in the same paper on hypergeometric series, in his great memoir on the hypergeometric series of 1812. In that same memoir, you will see this appearing for the first time. Legendre gave this formula, duplication formula, in 1809. 3 years later, its generalization appears. Correct? This can be generalized even further. 70 years later, in 1884, Schlabach generalized this formula even further, and Schlabach's formula takes the form of a reciprocity law. You can refer to that in the paper in the monthly paper that I sent you, the reciprocity formula of Schlabach. So, this is Gauss's formula. Well, one can prove the Gauss's formula exactly as one proves the duplication formula using Wheeland's theorem. Exactly as you did the Wheeland's theorem, imitate the proof of the duplication formula to prove the Gauss's product formula using Wheeland's theorem. That is an exercise for you. You will of course need the normalization. The normalization condition is difficult here, and what you need is this formula, root n gamma 1 over n, gamma 2 over n, etc. Gamma n minus 1 over n is 2 pi to the power half n minus 1. This I am leaving as an exercise for you to deduce from the reflection formula. Compute the square of the left hand side, take the square of the left hand side and regroup the terms, right. Gamma 1 over n, gamma n minus 1 over n. Use the reflection formula. Gamma 2 by n, gamma n minus 2 by n. Use the reflection formula for this pair, etc. You will need this for the normalization when you try to prove the Gauss product formula. Shall we proceed? All right. Let us go further. Several proofs of the Euler's reflection formula are known to you, are known in the literature. I explained a proof due to Dirichlet. There is a proof due to Dedekind. Dirichlet gave two different proofs. Another proof of Dirichlet is also available using the integral representation. And very strangely, one of the most authoritative account on the gamma function was written in 1905. It is in German. But this was written by Niels Nielsen. It's a very scholarly account. He spent about 20 years of intense research looking at the literature in several languages. The literature is scattered in Russian, Italian, German, French, Danish, Latin, several languages. And so Niels Nielsen has done a very thorough literature survey, but nevertheless he has overlooked Dedekind's thesis. It doesn't, there is no mention of Dedekind's thesis at all in this book, which is somewhat very remarkable. It's an obvious oversight. I mean, it's like there is so much out there that it is easy to miss out. What is very remarkable is what he has not missed. The amount that he has consolidated, that is really remarkable. Niels Nielsen's work. The proof of Dedekind, which we are going to discuss now, appears as a guided exercise in a very important book by Askey, Andrews and Ranjan titled Special Functions. It is published in the Cambridge University Press. This is a very important book on special functions. Askey, Andrews and Ranjan. Andrews, of course, is a great combinatorist, George Andrews. He is a great mathematician. And Askey, all three are remarkable, but Andrews' name will probably familiar because of the if you Ramanujan identities. That's more familiar to us. Okay, so let us turn to the proof of the reflection formula of the proof of Dedekind. Okay, now we begin. We'll call for abbreviation. We should first note that let us call beta of a comma 1 minus a. Let us call as beta of b of a. Let us begin with this little abbreviation. You need. I can't go on writing beta a comma 1 minus a everywhere, that is too cumbersome. So, let us simply call it b of a. B of a is a symmetrical function, b of a equal to b of 1 minus a. So, when you differentiate and put a equal to half, what do you get? B prime of half equal to 0, absolutely straightforward. And then it is also well known that b half is pi, that is elementary, right? Beta of half is pi. Alright, differentiate it twice. Remember that what is b of a? Remember that exercise, integral 0 to infinity t to the power a minus 1 dt upon 1 plus t. Differentiate under the integral twice. Remember we had discussed this differentiation under the integral sign.